talk about subspaces. To do so, let's do a quick review of what a vector space is. In this course, we'll always let F denote a field. We're not really going to worry about defining what a field is in a very general sense. We'll only say that our field will be one of three types. Either it'll be Q, the collection of rational numbers, R, the collection of real numbers, or C, the collection of complex numbers. If you ever get confused, you can just simply think that F is just R, the real numbers. Nothing will really change if you don't think of it that way. We're going to be interested in three objects. First, a non-empty set V. Second, an operation plus that will be called vector addition. This will take two vectors, call them x and y, and return a third vector that will denote as x plus y. And finally, an operation dot that will be called scalar multiplication. This will take a number, say call it c, as well as a vector x, and it'll return c times x. Given these three, we'll define a vector space over F as a triple satisfying the following 8 axioms. First, we need to make sure that we have commutativity, that is, that the order in which we do vector addition does not matter. Second, we need associativity. Remember that vector addition only combines two vectors at a time, namely x and y, to form x plus y. So we need a way to combine three or more. That's the idea of associativity. Third, we need an identity. That is, that there should be an element that we'll call the zero element, call it capital O, such that x plus O is x for every element x in V. Fourth, we need an additive inverse. What we mean by that is, given a vector x, there should be another vector, which we'll call negative x, such that x plus negative x is our zero element, capital O. We'll need to make sure that if we scale any vector by the identity, then we just get back to where we started from. That is, 1 times x should be x for any vector x. Next, we need to make sure that there is a way in which we can define scalar multiplication in a nice way. So given two scalars a and b, we can first take a times b, which will be another scalar, and then scale that to a vector x. So parentheses a times b, parentheses times x. That should be the same as a times parentheses b times x. That is, we can first scale x by b, then scale that resulting vector by a. We finally need to combine these two operations, vector addition and scalar multiplication, in a compatible way. So first, what we could do is add together two vectors, x and y. Then we can scale by a vector a. That should be equivalent to scaling x by a, scaling y by a, and then adding those two resulting vectors together. And finally, we need to make sure that if we add any two scalars, a and b, and then multiply that by a vector x, this is the same as first scaling x by a, scaling x by b, and then adding those two resulting vectors. With all of this in mind, remember that we will call the elements a in our field F to be scalars, and we'll call the elements x in our set V to be vectors. This is just simply a matter of notation. Don't really confuse the vectors here with what we defined in the previous lesson. Let's go over some examples of this as we did last time. We can consider the collection of m tuples. This here is an example of a vector space. Remember that the addition and scalar multiplication are both defined component-wise, as you see here on the screen. This is our usual standard definition of a vector space. We can generalize this slightly by considering m by n matrices. Remember that an m by n matrix is just an array of numbers where we have m rows and n columns. This is also an example of a vector space. This just generalizes what we had before with m-dimensional vectors. Here, just like before, we just have vector multiplication, vector addition, and scalar multiplication defined component-wise. You'll notice that the matrices here we will also call vectors. Again, we're just generalizing the concept, so try not to get confused here when we say the word vector. We just mean that it's just an element from a vector space. We saw before a rather strange example. Let's consider the first quadrant of the real plane. By the first quadrant, we mean that we want a vector such that the components, namely a1 and a2, are both positive numbers. We know that this is not a vector space if we use the usual vector addition scalar multiplication. Really, this is because the axioms dealing with the additive identity and additive inverse fail. That is, that the origin 0, 0, which was our 0 vector, is not an element of the first quadrant. Similarly, if we had a vector 2, 3 that is sitting in the first quadrant, its additive inverse, namely -2, -3, is not in this vector, in this space. However, we can define new operations so that we do have a vector space. Let's define them here as circle plus and circle dot. Circle plus will be defined by multiplying the corresponding coordinates, and circle dot will correspond to exponentiation of the various components. So in this case, our, quote, 0 element, unquote, would be the vector 1, 1. The way that we found this was by keeping very close tabs on the definition at hand, on circle plus and circle dot. So again, with these new definitions, we actually do have a vector space. This example here is just meant to emphasize that we have to be very careful as to the triple. It's not enough to say that the set V is a vector space. We really need to know the set V as well as vector addition and scalar multiplication. Now here's a basic question. Say that someone gives you these three, a set V, R plus, and R times. How do we prove that such a triple is a vector space? Well, this is the concept that we're going to see quite a bit over the next few lessons. So let's start with the motivating result to get an idea of how this might work out in practice. Say that we already know that we have a triple, V plus and times, that is a vector space. Then I'll give a new way of showing that a subset forms a vector space. My claim is that the following two statements are equivalent for any subset W of V. By subset, what we mean is every element of W is necessarily an element of V. First, the triple is a vector space over F. That is equivalent to saying that the following three properties hold for W. First is that the 0 element is actually in W. We know that the 0 element exists in V, but the statement is that it actually should exist in the smaller set W. Second, we need closure under vector addition. What that means is, given any two elements, X and Y in W, the sum must also be in the smaller set W. And third, we need closure under scalar multiplication. What that means is, given a scalar C and a vector X, then the product C times X must be in the smaller set W. If either of these holds, either statement I or statement II, then we'll say that such a subset is a subspace. A subspace is just a concatenation of the phrase subset that is a vector space. Let's try to discuss a little bit how would you prove something like this. Well, we used this phrase earlier, if and only if. It's what's called a biconditional. That means that if statement I holds, then statement II holds. Conversely, if statement II holds, then statement I holds. Notice that we are not assuming that both must be true. We're simply saying that if one is true, then the other must be true. That's the idea of a biconditional. So that means that we actually have to show two directions in order to prove this theorem 1.3. So first, let's assume the statement I is true. That is, that our triple is a vector space. We're going to use this assumption to prove that statement II is also true. Well, remember that II has three parts A, B, and C. So we'll focus on showing that those three must be true. Well, by axiom VS3, that is, it has an additive identity, we see the statement IIA must hold. That is, that W does contain the identity element. By the definition of vector addition, plus, we know the statement IIB must hold. That is, that W is closed under vector addition. Similarly, by the definition of scalar multiplication, we see the statement IIC must hold. Well, now, since we've shown that A, B, and C must hold, we conclude the statement II must be true. We've just shown one direction of this biconditional. Next, let's assume the statement II is true. We're going to use this to show the statement I is true. That is, that we really have to show that this triple here is a vector space. Well, in order to do this, the first thing we have to do is make sure that we actually understand what all three of these mean in the triple, W, plus, and times. So let's just be very careful about that. Well, because statement IIA holds, we see that W is a non-empty subset. So we're going to be very careful about this. W must be a non-empty subset. It's not empty, of course, because statement IIA means that the zero element must be in W. Well, statement IIB means that vector addition holds for W, so there is an operation plus. And similarly, statement IIC is assumed to be true, so there is this idea of a scalar multiplication, namely dot. So, before we can go any further, we now know that we at least have a triple we can work with, this plus, dot, and the set W. So we have to verify that all 8 of our axioms actually do hold for W. So let's just try to discuss a few of these here. Let's take a look at vector space axiom 1. This was the one with commutativity. Well, we know that this holds for everything in V, namely x plus y is equal to y plus x for everything in V, so it must hold for every subset of V, namely x plus y is equal to y plus x for everything in W. So this means that we can certainly say that axioms VS1, VS2, VS5, VS6, VS7, and VS8 all hold. So this means that we're only missing a couple, namely VS3, which is the identity, and VS4, which is additive inverses. Once we know that these two work, then we're done. To this end, we first are going to show that the zero number times any vector x is the zero element, right? That is 0 times x is capital O. And we'll show that -1 as a number times x as a vector is equal to -x, namely the additive inverse, for every x in W. Right? Once we show these two, then we can actually conclude that axioms VS3 and VS4 hold. So let's first try to prove that VS3 must hold. To this end, pick any vector x in W, and let's let y be the additive inverse of 0 times x. Now we're assuming that y is in V. We're not assuming that it's in W. Of course, we know that V is a vector space, so its additive inverse, namely y, must exist in V. Similarly, let's denote -x to be the additive inverse of x. Again, x was in W, so -x, we know for the moment, will be in V. We actually want to prove that -x is in W, but we'll come back to this in just a moment. So first, notice that the additive identity, capital O, must be OX plus Y. This is because by choice, Y is the additive inverse of 0 times x. So by axiom VS4, for our vector space V, we know that 0x plus its additive inverse y must be the zero element. Next, we can use the fact that the zero number, not a vector, the zero number, 0 plus 0 equals 0, in our field F. Remember that we know that this holds for real numbers is the same idea here. Now we can use distributivity to see that if I take 0 plus 0 as a number times x as a vector, this must be 0 times x plus 0 times x. Again, here we're using distributivity for our vector space V. Here, we can move around our parentheses based on associativity for our vector space V. So we see that 0 times x plus parentheses 0 times x plus our vector y must be equal to what we had before. Next, we see that 0 times x plus our additive identity, capital O, must be equal to what we had before because y is by choice the additive inverse of 0 times x. So again, we just use that 0 times x plus y must be the additive identity for the vector space V. But now, we realize that by the definition of additive identity, 0 times x plus capital O must just be 0 times x. So again, we're using the property of the additive identity for our vector space V. So we've used a variety of axioms for the vector space V to now conclude that 0 times the vector x is the additive identity capital O. So, since we're assuming that IIC is true, what that means is that our vector space our set W is closed under scalar multiplication. We can pick lowercase x in W, and we can pick a scalar 0. So then statement IIC means 0 times the vector x must be in W. Again, statement IIC means that W is closed under scalar multiplication. But we just showed that 0 times the vector x is the 0 element, capital O, so capital O must be in W. So we've actually shown now that capital O is in W. So axiom VS3 must hold for W. To be precise, we actually could have shown this in a different way, but we wanted to actually work through this statement here about 0 times x is capital O because we're actually going to use this in just a moment on the next slide. So we only have one more to go. Let's try to prove that W is closed under additive inverses. So to this end, we want to consider negative x. Again, x is an element of W, so let's consider negative x. Well, we know that negative x is negative x plus capital O because we know that the additive identity holds for the vector space V. Next, we just finished showing that 0 times the vector x is capital O, so we can replace our capital O from above. Now, we use the statement that 1 plus negative 1 is 0 as numbers in our field F. Remember that this is even true for real numbers. And we'll substitute this back in for the 0 in 0 times x from the previous line. Now, let's use distributivity for our vector space V. So we can say 1 plus negative 1 times x is simply 1 times x plus negative 1 times x. Now remember that 1 times x is equal to x for any element x. This was because multiplicative identity holds for the vector space V. Next, we'll use associativity to move around the parentheses, and we'll see that negative x plus x will be replaced now by the 0 element, namely capital O, because we're assuming that the additive inverse property holds for the vector space V. And finally, the axiom additive identity means that we can just ignore the 0 element, capital O. And so if we step back and look at what we've just shown, we've shown that the negative of x is actually -1 as a scalar times the vector x. But now let's go back and see how do we state things previously. Let's go back to statement IIC, where we were assuming that W is closed under scalar multiplication. So here we can scale by -1 to see that -1 times the vector x is in W, because -1 is a scalar, and because x was assumed to be in W. Therefore, -x is in W, which actually shows axiom VS4, namely additive inverses, holds for W. So putting all of this together, we can now conclude that the triple W plus dot is a vector space. Hence, statement I is true. So let's try to end things today by going over some examples to see how this really helps us to prove that a given triple is indeed a vector space. Our first claim is that if V is any vector space, then I can either take W, that subset, to be the entire set V, or I can let W be the singleton set consisting of just one vector. In either case, W is a subspace of V. So let's see why this is true. Well, if I wanted to prove that the W in these cases are subspaces, according to the previous result, we must verify 3 axioms. First, we have to verify that the zero element is in W. Well, we see that this is the case because if W were equal to V, then because V is a vector space, we see that V has the zero element, therefore W has the zero element. In the second case, if W were the singleton set consisting of just one vector, then again, we see that the zero element is in W. So in either of these two cases, we see that the zero element is indeed in W. Next, we have to check that we have closure under vector addition. Well, if W were equal to all of V, then we know, by the definition of vector addition, that given any two vectors x and y in V, then their sum is in V. Therefore, if x and y were in W, then the sum will be in W. In the other case, where W consists of just one vector, if I were to pick x and y in W, then x and y would have to just be the zero vector. I have no other choice. But we already know that the zero vector plus anything is that anything. So in particular, the zero vector plus the zero vector is the zero vector. So again, in this case, we see that if x and y are in W, then x plus y must be in W. This means that W is indeed closed under vector addition. Finally, let's take a look at whether we have things that are closed under scalar multiplication. Well, let's see. If W were equal to V, then there wouldn't be anything to show, just like before. So we really should take a look at the case when W consists of just one vector. That means it really comes down to the statement that any scalar times the zero vector is the zero vector. So this is what we're going to prove. C times capital O is capital O for any scalar C in F. So to get this to work out, just like before, let's let Y be the additive inverse of C times capital O. We're going to prove that Y is equal to the zero vector, but for the moment, let's just let Y be the additive inverse, whatever that element happens to be. Well, because the additive identity property holds for our vector space V, then we know that C times capital O equals C times capital O plus the additive identity. Next, we're going to replace capital O with C times capital O plus its additive inverse, namely Y. Next, we'll use associativity of vector addition to move around the parentheses. Next, we'll use distributivity to factor out that scalar C. Next, we'll use the fact that capital O plus capital O is equal to capital O to simplify things a little bit. And now we see that we have C times capital O plus Y is our original C times capital O. But Y was chosen to be the additive inverse of C times capital O. So they cancel, and we see that C times capital O is capital O, as what we wanted to prove. So this really does mean that we found what we set out for, which to show that W is indeed closed under scalar multiplication. Let's give another example. Say that we have the collection of M tuples, like the way we began the lecture. Remember that we know that this here forms a vector space where plus and dot are the usual vector addition and scalar multiplication, respectively. We're going to form a rather strange looking subspace. Fix a vector n in our set V, and let's consider the following subset. Here we'll let the vector n be the M tuple that has components a1, a2, so on and so forth down through a sub m. And let's let W be that subset of V that's defined as the set of solutions to one equation, namely a1 x1 plus a2 x2 plus so on and so forth plus a sub m x sub m equals 0. Again here, the a1, a2, and so on and so forth are fixed once we let n be a fixed vector. The claim is that this W is a subspace of V. We give this a name. We call W a hyperplane going through the origin. Now there is a nice geometric interpretation of this. Let's consider the special case where our field F is the real numbers, and let's let M equal to 2. That is that V in this case is just the real plane. We like the real plane because we can draw pictures with it. The W in this case consists of vectors x comma y such that ax plus by equals 0, where n is just the vector a comma b. Again here, n is fixed, and then we just take a look at W. Geometrically, this W is nothing more than a line through the origin. You can see here on the slide that we have a few different examples of lines. Line C is in green, line B is in red, and line A is in blue. Well, these three lines will correspond to different choices of this vector n. Those of you who've taken vector calculus may notice that n is essentially the same thing as the normal to the line. So simply put, what the previous statement says is that if you're given the real plane R2, any line going through the origin is a subspace. So the picture here shows at least 3 different examples of subspace: the blue line A, the red line B, and the green line C. Those are 3 different examples of subspaces in the real plane. So let's try to skim over how one actually does prove this proposition that hyperplanes are subspaces. Again, to prove that something is a subspace, we need to verify 3 axioms. First, we have to check that the 0 element does exist in this set. Well, if we take a look at the 0 vector from our vector space V, remember that that is an M tuple whose coordinates are all 0. So we have to make sure that that equation that cuts out W is satisfied. Well, if I plug in x1 is 0, x2 is 0, so on and so forth, then I see that a1 times 0 plus so on and so forth, am times 0 should all equal to 0. Since that equation is satisfied, we see that the origin must exist in our set W. Therefore, W has a 0 element. Next, we have to check that W is closed under vector addition. Well, let's take any 2 vectors, x and y, from W, and let's add them together. We know how to do this because we know that vector addition in this case is just defined component-wise. Now, the claim is that this sum, x plus y, is in W, the reason being that it has to satisfy the extra condition that defines W. Namely, I need to take A1 times the first component plus A2 times the second component, so on and so forth, and make sure that I get back 0. Well, you can check this based on the equations here on the slide. Finally, we have to check that W is closed under scalar multiplication. Well, again, remember that the definition of scalar multiplication comes about by the components. So we just have to make sure that the scalar multiple c times x is also in W by just checking that it does satisfy the extra condition. And in this case, it's a matter of saying that A1 times the first component plus A2 times the second component, so on and so forth, all adds up to 0, which you can do by just checking the equations here on the screen. Now, we've given some examples where this theorem does allow us to determine when a set is a vector space. Let's end by discussing an example where we cannot use the theorem to determine that a set is a vector space. Well, we've seen that the real plane, namely R2, is a vector space where plus and dot are the useful vector addition and scalar multiplication, respectively. Let's go back to an example that we used when we began the lesson. Namely, let's take a look at the first quadrant of the real plane. Here in the diagram, this will be the upper right that we're denoting as quadrant 1. This W here consists of those vectors where the components A1 and A2 are both positive. Clearly, this here is a subset. However, we've seen that this is not a vector space because axioms Vs3 and Vs4 failed. We discussed this at the very beginning of the lesson. So this W here is not a vector space. Now, we can choose new operations to make W a vector space. We started the lessons by discussing these weird operations that we defined as circle plus and circle dot, where circle plus comes about by multiplying the components, and circle dot comes about by exponentiating the components. Notice that even though we do have a vector space, unfortunately, we cannot use Theorem 1.3 to prove that this is a vector space. Simply put, Theorem 1.3 says we can only show that something is a vector space if it's a subset of something that we already know is a vector space. In this case, we don't know that V under this new circle plus and this new circle dot is a vector space. In fact, we haven't even explained how to define circle plus and circle dot for V. We've only explained how to define these two operations for W. So unfortunately, we cannot use Theorem 1.3 because we don't yet know that this larger set, V under circle plus and circle dot, is a vector space. Although we do know that W is a vector space under these operations, we just cannot use that theorem in order to conclude this. So thanks very much for your time, and next time we'll discuss a little bit more of some of these examples of vector spaces.